Hey guys, hello everyone. So welcome to this module 5 of digital image processing. In module 5 we will be discussing about the important concepts like image segmentation and its algorithms. So please watch the video till the end. First, let us study about what is a segmentation. So segmentation is basically you can say it's a process of partitioning of an image into its multiple regions, and you're extracting all the meaningful region from it. So what you are doing is you are just taking an image, you are dividing into its various regions, and you are finding out some of the other important features from that image, which is nothing but a region of interest. Okay, and for doing that stuff you need a image segmentation algorithm also, which works on similarity as well as discontinuity principle. So what is the discontinuity principle first? So here what we do is we extract regions that are different in properties like intensity, colors and textures. And similarity principle, what we do is we are grouping the pixels based on a common property. So this is the formal definition. For example, if I consider this as a complete image, 20 20 20 10 10 20 20 20 10 10 20 20 20 10 10 15 15 15 15 15. So you can see, like, if I want to segment this particular image, I have to segment this on the basis of a particular property. So what I'll do is here we are collectively partitioning, you can say, or I should say I'm clubbing the entire image based on common parameters. For example, if it is having 20 20 20, just club the entire region of 20, then again the same region of 10, and again the same region of 15. This can be further be corresponded as this 20 region is represented as R1, followed by this 10 is represented by R2, then 15 is represented by R3. Now what are the characteristics of this particular image? You can see if the subregions, like all these are my subregions, if they are combined together, then we obtain the original image. Yes, that's true, because obviously if the image is composed of this kind of pixels, we are grouping them in such a way that if I take the union of all this pixel, I should get my original image back. Okay, and next we have a subregion should be connected. That means there should not be any opening traces. Next, the regions are, for example, R1 and R2. For you can see R1 value was all 20, R2 value was 10. So we have distinguished them as 20 and 10. That means make sure ki all the three regions will have do not share any common property. They have some different properties like the value of pixels. Also, the last one says that each region satisfy a predicate which satisfies a grayscale value, texture or any other image statistics, which you will get to know later in this video. First is how will you classification of image segmentation. So basically image segmentation is based on two parameters. First is the user interaction, next you have the pixel relationship. In user interaction, what you are doing is you are basically distinguishing them into three parts, that is manual, semi-automatic and automatic. Next is pixel relationship, you are doing on based of contextual or non-contextual. So let's move forward. So based on user interaction, guys, it is basically divided into manual, automatic and semi-automatic. In manual, what you are doing is, it involves an expert who is observing and tracing the region of interest boundaries of an object using a software. So like here you have seen earlier, you are basically tracing this particular image on the basis of some common parameter. Here also you are doing the same thing. You are tracing the region of interest boundaries using a software, and this software makes the segmentation decisions. The control points and the splines mainly help in maintains the boundary integrity. The process is subjective and time consuming and susceptible to human errors. So what happens is, like, once you segment the image on basis of a common decision, we have something known as control points and splines. This will help you to maintain the boundary integrity of a particular image, and then also the process is very much time consuming and it is also susceptible to human errors. Sometimes you might face errors while doing it. Next we have is automatic. Automatic, what it is happening is they segment the structure of an object without any human intervention. So here what happening is, in manual you are taking a help of there was an expert who was observing the tracing the region of interest, and he was just segmenting the image on the basis of some common properties using this software. But in automatic, the person is not at all involved. It's the software itself who does all the things, and generally it is carried out for large number of images. Okay. Next is semi-automatic. Semi-automatic, they mainly start with a manual input, for example seed points, and then they proceed automatically. So here what happens is you are giving a manual input from the beginning, and then the process starts automatically. then there is always a strike balance between a manual as well as fully automatic methods, because it basically uses the humans in the initial step, and later you are using the software to make you segment the region of interest. Also, what is the name of the algorithm for semi-automatic segmentation is also known as assisted manual segmentation algorithm. Just remember the name of this algorithm, guys. We don't have to study this algorithm in detail. Just know the name for the VTU exam. Next we have is, like, first we have distinguished on the basis of user interaction, then we have based on pixel relationships. So in pixel relationship, we are distinguishing them into contextual and non-contextual. In contextual, what you are doing is, it is basically region-based algorithms. You are grouping the pixels on some shared properties and relationship. So basically, the pixels are mainly grouped into mainly grouped that are having some common properties, and then their aim is to form a homogeneous region by exploiting the pixel similarities. Just remember the application, it is mainly used in clustering. Also, we have is non-textual. Non-textual are the pixel-based algorithms where the focus is mainly made upon the individual pixels and local features without considering the pixel relationship. So it is mainly help you detect all the discontinuities like edges and isolated pixels. For example, it is using edge detection algorithm. Just remember this application, guys. It's very much important. Also, just remember what is the basic definition. Contextual is all region-based algorithms where you are grouping pixels based on a certain properties, whereas in non-textual, what you are doing is you are focusing on the individual pixels but not considering any pixel relationships. Moving forward, next we have detection and discontinuities. First we have is point detection. So point detection, what you are doing is a technique to identify isolated points in an image where the gray level is significantly different from the surrounding background in a homogeneous area. Okay, so let's understand this with the help of this figure. You can see it's basically a 3x3 matrix only: Z1, Z2, Z3, Z4, Z5, Z6, Z7, Z8, Z9. Let us consider it represents a form of an image. So if we want to, so I need a mask. This mask is superimposed on an image and a convolution process is mainly applied. So this is the formula: R equal to epsilon of k equal to 1 to 9 zk and f of k, where f of k is the gray level values of pixel associated with the image. Your threshold is applied because you have already studied, like, when you are trying to produce a grayscale image or a binary image, you have to apply some threshold. So now once a point is said to be detected at the location on which the mask is centered, where t is a non-negative image. So as the definition says, like, point detection, you have to make sure like this, it is different from the surroundings. Yes, you can see this example. Like, if I consider this as the center of the pixel value, you can see like all neighboring values are all different. So this is a proper example of point detection. Fine. So next we have is line detection. Line detection basically uses 4 masks are used to get the responses in R1, R2, R3 and R4 for directions in the horizontal as well as vertical area, that is plus 45 degree, minus 45 degree. So it's very easy to remember this matrix, guys. You have to what is the trick? Basically, suppose m1 is the first mask, you have to remember this values: -1, -1, -1, 2, 2, 2, -1, -1, -1. So for m2, for the second mask, what we are doing is we are just taking the transpose of it. That means the row becomes column and the column becomes row, that is -1, -1, -1, 2, 2, 2, -1, -1, -1. At the same time, for m3, what you are doing is, remember one thing very properly. For example, in m2 you have seen, you have taken the transpose, right? In m3 you are just shifting the value of this 2 towards your left. That means it is one by one, it is getting shifted down and up. So m3 will be, this 2 comes here, this -1 will come here, and this -1 will go up. So 2, -1, 1, -1, -1, 2, 2, -1, -1. At the same time, perform the next shift again. It will become -1 comes here, -1, -1, 2, -1, 2, -1, 2. Okay, so we have already seen what is m2, what is happening. In m3, what we are doing is we are just shifting this value of 2. Is 2, -1, -1, -1, 2, -1, -1, -1, and 2. For representing m4, what we are doing is just reverse it back: -1, -1, and 2, -1, 2, -1. That is, this will remain as it is. This will go up and this will come down to -1, -1. Next, let's see. Next we have is edge detection. Edge detection is basically a set of connected pixels that lies between the boundary between two regions that differ in the gray value. So edge is mainly extracted by computing the derivative of a image function. So this basically consists of two factors, that is magnitude of the derivative as well as direction of derivative. Magnitude of derivative, what it does, it is indicates the strength and contrast of the edge, and direction of derivative mainly helps you to measure the edge orientation. So this was quite theoretical. Let's understand the different types of edges. We have four types of edge: step, ramp, spike, and roof. In step edge, you can see this is the way of representing it. This is the way of representing a step edge, abrupt intensity change. So by step edge says it has an abrupt intensity change. For ramp edge, it's a gradual change in the intensity. For the spike edge, we have a quick change and immediately back to its original intensity. Then roof edge is like not instantaneous over a short distance. That means the pixel width doesn't remain fixed for a particular period of time. It gets changed simultaneously. Now next guys, very important, the flow chart or the stages of edge detection. First, let's start with the flow chart. First we have a start. You take the input image, then you perform filtering operation, followed by that we have the differentiation, then we have is localization, then you display the image, then you end the algorithm. So basically these three are the main three stages, that is filtering, differentiation, and localization. This is one of the very important question guys when it comes about explaining the stages of edge detection. So let's understand in the process. Okay, so let's see about all the stages of edge detection. First we have is filtering. Filtering, what it does is it filters the input image to get the maximum performance for the edge detectors. So what it does is filtering will perform two major operations. First is smoothing, then we have a Gaussian filter. The smoothing will help you to reduce the noise while preserving the important edges. At the same time, the Gaussian filter will, what it will do is it will apply the Gaussian function. It will blur the image and then it will reduce the noise. And what is the benefit is it will enhance the quality of the edges. That was all about filtering, where you are just filtering the image to get the maximum performances by applying two major operations, that is smoothing and Gaussian filter. Smoothing will help you to reduce the noise by preserving the important edges, whereas the Gaussian filter will apply the Gaussian function and then it will blur the image and then reduce the noise. Next we have is differentiation. Differentiation is, so let's understand this first order derivative and second order derivative, which comes under differentiation in detail. So what is the first order derivative? Basically it will help you to measure the rate of change of intensity of pixels. So basically it will do is it takes the difference between the two neighboring pixel. If it is 0, it indicates that there is no transition, and if there is no transition, there exists not a single edge. Okay, so how will you represent this in a form of a mathematical equation? We are assuming that f of x is a continuous function, del f upon del x equal to limit x tends to 0 f of x minus delta of x divided by delta x. Remember this equation guys. For a discrete image, the change of delta x is always 1. The discrete first derivative is measured by, now how will you measure this discrete derivative? Delta of x equal to f of x minus 1 is, if they did nothing but they have just put the value of delta x is equal to 1. If you put delta x is equal to 1, the equation becomes delta x equal to f of x minus 1. Now what is second order derivative? Second order derivative is basically checks for changes in the first order derivative, like whatever changes you have done in the first order derivative comes into the second order derivative only, and significant changes in the value of the first order derivative indicates that there is a presence of edge. So let's understand this with the help of this very good question. We have consider a 1D image f of x equal to 60, 60, 60, 100, 100, 100. What is the first order derivative as well as second order derivative? So let's solve this question guys. Okay, so this was the question. 60, 60, 60, 100, 100, 100. So let's take the first order derivative. First order derivative will be very simple. You have to just do the just take the difference between this 60 minus 60 0, 60 minus 60 0, 100 minus 60 is 40, then 100 minus 100 is 0, then again 100 minus 100 as 0. So this is the first order derivative, guys. Just take the difference between the second and the first. Similarly, second and the first, this minus this. Okay, this is the first order derivative. So how will do the second order derivative? Second order derivative is nothing but you have to take the difference again. Okay, so if you take the difference again, the equation becomes 0 minus 0 again 0, then 40 minus 0 is again 40, then 40 minus 0 40, then 0 minus 40 will be minus 40, then 0 minus 0 will be again 0. Now you can see there is a significant change in the value of the pixel. You can see this was my first order derivative, now this is my second order derivative. Here it was 0, here I have got a 40. Now this 40 indicates that I have a edge. Okay, and now also I have got a negative value here. You can see minus 40. Now this minus 40 will indicate a 0 crossing. That's what about this question. What we have done is this array was given to us in the question only. They'll provide this first order derivative, just you have to take the difference. Now what is the formula? Formula is basically, just write this formula in exam, f of x plus 1 minus f of x. It's nothing but you are taking the first, if I consider this as f of x, this is a f of x plus 1, f of x plus 2, and this way it continues. Just take this minus this, then this f of x plus 2 minus of f of x plus 1 continues till the same. Once you get the first order derivative, apply the same logic again in. So let's see what is the gradient of an image. Gradient of an image is mainly represented by delta f of x comma y will be dou f of x y upon dou x divided by dou f of x comma y by dou y. So you can represent this dou f of x comma y upon dou x as gx. Similarly for dou f of x comma y by dou y as gy. So this is the equation where gx is nothing but dou f upon f of x comma y upon x. This is upon y. The magnitude of the above vector is nothing but you will take the square root of gx whole square plus gy whole square. Then you have a gradient approximation with the absolute value. Gradient approximation is mainly represented as dou f of x comma y as the maximum value of gx and gy. So you have to take the maximum value of gx and gy. Then you have a gradient direction. Gradient direction is theta equal to tan inverse of gy by gx. So guys, you have to remember all these equations, and there is no as such a proper derivation of all these equations. It's not there in your syllabus as per the scheme. So just you have to remember all these formulas and write it when the question comes whenever this question comes in an exam. Next is localization. Localization, what is localization? Localization is all about the final stage of the edge detection, where you are finding the exact edges and ensure whether they are sharp or well defined or continuous. So here you are getting the exact position of where my edge is lying, and then we are also confirming whether it is well defined or it's continuous. Also next we have something known as normalization. Normalization, what it does is normalization will scale the gradient value to a range of 0 to k. It helps to standardize the gradient magnitude across the different images. Basically what it will do is it will help you to scale a particular image to a particular range of value, and it helps you to standardize the gradient magnitude. Okay, so we have a formula also for this. You should remember n of x comma y will be equal to g of x comma y by max of I equal to 1 to n into g of I comma j into k, where k is constant and is set to a value like 100. Also the edge map e of x comma y equal to 1. It can be either 1 or 0. 1 when n of x comma y is greater than equal to t, or 0 otherwise. Next we have is the edge detection algorithms. Edge detection algorithms, you can I would say it is differentiated into some 4 categories. First is derivative types. Next we have template matching. Then we have Gaussian derivatives. Then we have pattern fit approach. In the first order edge detection operators, you will see what it will do is it is same as we have studied before. It's like it identifies the edges by measuring the intensity gradients. So based upon the difference upon the intensity values, it will help you to identify the edge, and the operators which will help you to find out the first order derivative is nothing but a differential geometry as well as the vector calculus, which will help you to find the rate of change of intensity of image. So delta equal to dou upon dou x by dou upon dou y. So when this is applied to any of the image function f, so dou f will be equal to dou f upon dou x divided by dou f upon dou y. Now this resultant value will provide me the rate of change of intensity of the gradients, and the same way will represent and in the same equation format. This magnitude equal to, you can see, delta f of x comma y equal to max of dou f upon dou f of x comma y, that is equal to dou f upon dou x whole square upon dou f upon dou y whole square. At the same time, theta is equal to tan inverse of dou f upon dou y divided by dou x upon dou y. Then next we have something known as discrete approximation. You remember this formula, backward difference. Backward difference is represented by f of x minus delta x upon delta x. Moving next, when the delta x value is 1 for discrete image, then the mask becomes 1 comma minus 1. For the same for forward difference, the formula gets changed for f of x plus delta x minus f of x upon delta x. The same time when delta x is 1 for discrete image, the mask becomes f of minus 1 comma 1. Same time when you take central difference, is nothing but you are adding all the you are adding the forward and the backward difference. Once you add this, that is f of x plus delta x minus of f of x minus delta x by 2 delta x. Okay, so when delta x equal to 1, the mask value becomes half of this 2 will come outside, 1 0 minus 1, whereas when you want to extend it to a 2D image, gx will be equal to dou f upon dou x and gy will be equal to dou f upon dou y. That was that was all about how to define a first order edge detection operator. Now also this we have already studied, the first order edge detection operator. Now let's see how. Okay, so let's see about the Roberts operator. Roberts operator, what it does is it will calculate the gradient by computing the difference between its adjacent pixels. Okay, so for that you need a Robert kernel. A Robert kernel, what it will do is it will compute the gradient with respect to its diagonal elements. Okay, so if I want to calculate the gradient components gx and gy, so gx will be equal to dou f upon dou x, that is z9 minus z5, gy equal to dou f upon dou y z8 minus z6. Suppose this is my grid, z1 z2 z3 z4 z5 z6 z7 z8 z9. So Robert's kernel process will be z9 minus of z5 and z8 minus z6. Then mask value, that is nothing but gx minus 1 1 0 0, gy will be equal to 0 0 minus 1 and 1. Then dou f of x comma y equal to magnitude of the dou f upon x comma y. This is nothing but square root of gx whole square upon gy whole square. Then same theta is equal to tan inverse of gy upon gx, and the absolute value is represented by mod of gx plus mod of gy. So what is the algorithm for this generic gradient generic based algorithm? You have to write this algorithm when it comes to explain about Roberts operator. So first is you read and smooth the image, you convolve it with g of x, then you convolve with g of phi. The convolution formula is f of x equal to f into g of x. For g of phi, it will be f into g of phi. Then you compute the edge magnitude and orientation, and then you compare the edge magnitude with the threshold. Next we have is Prewitt operator. Prewitt operator, what it will do is it will compute the gradient by taking the central difference of neighboring pixels and apply averaging to the reduced noise. That is, for a 1D image it becomes dou f upon dou x equal to f of x plus 1 minus f of x minus 1 by 2. Dou f upon dou x for 2D image will be dou f of x plus 1 comma y minus f of x minus 1 comma y upon 2. This is nothing, guys. Basically we apply central tendency formula. So this is about Prewitt's operators. Now how will you apply the approximation? How will you represent it? So this can be mainly uses a 3x3 mask to reduce the noise. So delta f will be equal to z8 plus z7 plus z8 plus z9 minus of z1 plus z2 plus z3. Just keep the brackets and put the modulus function, plus z3 z6 z9 minus z1 z4 z7. So how did we perform this? If I consider the same thing, same grid, it is z7 z8 z9 minus of z1 z2 z3. This we take the difference, again plus of z3 z6 and z9 minus of z1 z4 z9. So this minus this plus this box minus this box. Okay, so the edges in x direction, the mx and the mask in x will be equal to minus 1 1 minus 1 minus 1 minus 1 0 0 0 1 1 1. The same time for y, just take the transpose of this minus 1 minus 1 minus 1 0 0 0 1 1 1. Next we have is a Sobel operator. Sobel operator, what it will do is, Sobel operator is basically, you can say it's an improvement or you can say an advanced version of the Prewitt operator only. It will incorporate the reduce noise and they use central dependencies for gradient approximation. So guys, the same formula only, the same you can say representation as compared to the Prewitt operation. What we are doing is in the middle, you can say that in the middle value are just multiplying it with 2, like z7 plus 2 times of z8 plus z9 minus z1 plus 2 times of z2 plus z3 plus z3 plus 2 times of z6 plus z9 minus z1 plus 2 times of z4 plus z7. So what is the mask you have to represent? Mx will be equal to minus 1. Just we have performed a double operation. This you have to put minus 2 minus 1 0 0 0 1 2 1. For y direction, just apply the transpose to it. Will be minus 1 minus 1 minus 2 minus 1 0 0 0 1 2 and 1. Moving forward. Now also additional mask can be applied in horizontal direction. For example, 0 0 like 0 1 2 0 minus 1 2, like just make sure like if this 0 is the central pixel, you have all this common 1 1 1 elements at the same time. For my value also, it's just additional mask, guys. The main thing you have to remember is this thing only, the mx and my. Okay, this mx and my matrix you have to write it when it comes about the Sobel operator. Next, template matching mask. Template matching masks, what are these masks? Basically they are mainly direction sensitive filters which will help you in detecting the edges in a very specific direction. So first we have is a cursed mask. Cursed mask, what it will do is it will detect the edges by applying 8 different masks. 8 different masks in the sense, if we consider the compass direction, we have north, south, east, west, northeast, northwest, southwest and southeast. So you can see, like if I can see, I show you this entire matrix, we have some 7 matrices which you have to remember for representing each and every direction. For example, this is my k0, it's my initial, minus 3 minus 3 5 minus 3 0 5 minus 3 minus 3 and 5. For north, for k1 for northwest, what we are doing is just keep on shifting the pixel values towards your left. For example, you can see minus 3 minus 3 minus 3 and 5 was there, no? So if I shift this value of 5 towards my left, again you have to keep on doing a left shift continuously such that all the pixels get shifted one to the next position. For example, you can see if I shift my 5 here, now the 5 came here and the below 5 came up. So the same way, minus 3 5 5, this minus 3 came down, and you can see like this minus 3 which was present here, it has shifted to this corner. So it was minus 3. This is about k1, that is northwest. And the same time for k2, keep on performing this operation, guys, unless and until you get this matrix in k7. When you will perform, you will get this you will get this matrix. Okay, so this similarly k2 is for west, for southwest, south, southeast, east and northwest. So same thing for cursed mask. Whenever they ask you in the exam, just mention it is used to detect the edges by applying the 8 different mask method. You have to draw all this 7 k0 to k7, that is all the 8 matrices, mentioning which direction represents what. Okay, next we have something known as Robinson's operator. Robinson's operator is same as that of Kersh mask itself. It will also help you in detecting the edges with respect to a direction. I have just given for R0 the same value, the same continues for all the mask. For R1, again keep shifting this 1 will come here, again 0 will shift to here, minus 1 will come here, minus 2 will come here, minus 1 here. Keep on shifting the values one after the other in each and every matrix. Okay, then we have is Frei-Chen marks. Frei-Chen marks, what it will do is it will decompose an image into different components. Okay, so how will you decompose an image? So guys, it's very much it has very much less theory and more amount of matrices to remember. So try to remember all these matrices. I will put a flowchart of all the matrices and all the important questions in the next video, so please stay tuned. So f1 This is the first edge detection mask f1 upon 1 upon 2 root 2 1 root 2 1 0 0 0 minus 1 minus root 2 minus 1. So for f2 what you are doing is just take the transpose of this. Once you take the transpose of this, just this will turn ulta here. 1 root 2 1 0 0 0 minus 1 minus 2 minus root 2 minus 1. At the same time for f3 what you are doing is again you are performing this shifting of pixels. Well, how will you shift the pixels? Like minus 1 will come here, root 2 will come up like this. For similarly for f3 you did. At the same time for f4 what you will do is, for f4 you just perform the transpose, of this equation, that is root 2 minus 1 0 minus 1 0 0 then 0 1 root 2. Same for line detection also 1 by 2. This is the equation format to represent 0 1 0 minus 1 0 minus 1 0 1 0. f6 will be represented as this matrix, f7 by this, f8 by this. Then average detection marks, what you're doing is you're just taking the average of all, that is 1 by 3 of 1 1 1 1 1 1 1 1 1. So just remember all these matrices, guys. There is no as such any proper derivation or any proper expression required for the point of exam. Just remember why it is used and how to represent the matrix. That's it. Next we have is a second order derivative filter. Second order derivative filter, you can, what it is basically, delta into delta, that is second order derivative we are calculating dou upon dou x upon dou y into dou upon dou x upon dou y. So the equation becomes dou square upon dou x square plus dou y square upon dou square upon dou y square, with the delta and delta is delta square is the Laplacian operator. What it will do is it will produce double edges. At the same time it is too much sensitive to noise. Okay, so Laplacian of a so once you got the Laplacian operator, you are applying a Laplacian function to it. Now, the Laplacian function is mainly determined by delta square of f of x comma y equal to dou square f of x comma y upon dou x square plus dou square f upon x comma y upon dou y square. So few points to remember. Gradient is vector. The gradient is nothing but the vector itself, and we're applying two orthogonal filters. And next, Laplacian operator is scalar, that is a single mask is sufficient enough to carry out the edge detection process. Okay. So this is the derivation of your second order derivative. So guys, as per the syllabus, if you see, it says there is no derivation required, but to be on the safer side, I would suggest please go through the derivation once, because you can't predict what the question comes. So if I do a partial, what we are doing is we're just differentiating this equation like dou square f of x comma y upon dou y square. This can be represented as delta upon delta x upon f of x plus 1 comma y minus delta upon delta x f of x comma y. So with differentiation with respect to x, this becomes dou f of x plus 1 comma y minus f of x comma y minus of f of xy minus f of x minus 1 comma y. Just perform this minus operation. This minus and minus becomes plus. Similarly for y square, you have to do it for x square. At last, this equation you have to remember, that is f of x plus 1 comma y plus f of x comma y plus 1 minus 4f times of x comma y plus f of x comma y minus 1 plus f of x minus 1 comma y. This is the entire derivation for the second order derivative filters. Next, what is the algorithm? Algorithm is very much important, guys. You have to remember this. What you are doing is, first you are generating the mask. Once you generate, you apply the mask, and next you detect whether we have a zero crossing or not. What is a zero crossing? Basically a situation where the neighborhood pixel differ from each other in their sign. Okay, for example, if I consider this as my main pixel -4, you can see like the neighborhood pixels they differ from each other, right? They are not the same. So once what I am doing, this is the Laplacian mask. If I apply a rotation on this, what is the rotation we're doing is we are applying a rotation angle by 45 degree. That means that the extreme corner, you can see the phone neighbor of -4, that is 1 1 1 and 1. This will shift to the entire opposite corners, and the 0 0 will come as the you can say neighbors. Okay, so from Laplacian marks, you can see this one, all these ones have shifted to all the corners, and the zeros have come to its neighbors. Similarly, this is for variant 1. For variant 2, what they have done is they have just multiplied the value of, you can say, the first variant with 2. So just a normal variant you have taken. So let's take a normal pixel which is present in the center. provided that I have all my neighboring pixels are same. This is the first variant. For the second variant, we are doing nothing but doing the double of the image. That's it. Double of what? Just double of the you can say the 4 neighbor pixels. Okay. Next we have is the Laplacian operator, Laplacian of Gaussian, or also known as the Harman-Aldrich operator. What it will do is it will minimize the noise of the image. Okay, because once we are performing all the edge detection algorithms, the first thing which we have seen is you have to remove the noise and all, because noise generally distorts the image. So first we have to remove the noise. So how the noise is removed? At first you can see the image is blurred using a Gaussian operator, and then Laplacian operator is used. Then the Gaussian function reduces the noise, and the Laplacian minimizes detection of false edges. So whatever false edges are there in my image, everything will be minimized. So our main agenda will be to minimize the number of false edges and to reduce the noise from the image. So what is the derivation for this? Let's just consider that this is a Gaussian like for a 1D image, delta square of f into g will be represented as f into delta square of small g, that is f into Laplacian of Gaussian. Okay, so let us consider 2D function. 2D function is represented by g sigma of x comma y 1 upon root 2 pi of sigma square exponential of minus x square plus y square upon 2 sigma square. Okay, now what they have done is basically, now delta g sigma of x comma y into f of x comma y, you have just performed this equation f into g. So log you have performed. Now once the log equation is done, what we have done is we have taken the derivative of this, that is delta dou upon dou x of g of x comma y. Just apply the partial differentiation, dou upon dou x e to the power of minus x square plus y square upon 2 sigma square. So how will you solve this? Upon x, if you are solving it for x, it will become minus x upon sigma of x square e to the power of minus x square upon y square upon 2 sigma square. Guys, this is basic partial differentiation. I hope everyone is aware of this. At the same time, similarly you do it for the y also, that is dou upon dou x square g sigma upon x comma y can be represented as x square upon sigma 4 e to the power of minus x square plus y square upon 2 sigma square minus of e to the power of minus x square plus y square upon 2 sigma square. This can be further be represented as you can say x square minus sigma square upon sigma y to the power of 4 e to the power of this entire equation. Now what we are doing is, since my 1 upon 2 pi sigma square is it's a normalization constant, just ignore this, no need of this. So how will you ignore this? Just basically the log kernel is mainly described as log Laplacian of Gaussian equal to dou upon dou x square x g square of sigma of x comma y plus dou upon dou y square upon g sigma of x comma y is represented as x square plus x square and y square minus 2 sigma square, just adding these two, minus 2 sigma square upon sigma to the power of 4 e to the power of minus x square upon y square. So guys, very easy actually. First you just took for x you perform the log operation, for y you perform the log operation, and then you are just adding the first and the second equation to get the log kernel. Okay, next is what is the log algorithm. What is the algorithm says? We first generate the mask and apply the log to the image, and then you detect whether you have a zero crossing or not. Moving forward, difference of Gaussian filters. So log filters, as we have said in the previous slide, you can see that it can be approximated by taking two different size Gaussians. So g of sigma 1 of x comma y, this is one way of expressing 1 upon root 2 pi upon sigma 1 square exponential of minus x square plus y square upon 2 sigma 1 square. Similarly for g sigma of x2 also we take. Now what is the difference of Gaussian, that is DOG, is the difference between these two kernels. How we will do is g sigma 1 minus g sigma 2. You can see like 1 by root 2 pi we can take it as common. Okay, so 1 by root 2 pi we have taken as common. Put the square brackets, you can see under root of sigma 1 square was there. So taking the square, when the sigma 1 square comes out from the square, it becomes sigma 1, then e to the power of minus x square plus 2 sigma square minus 1 upon sigma 2 into minus of x square plus y square upon 2 sigma square. Just nothing guys, we have just done the difference between these two kernels and get this proper equation. Next we have what is the difference of Gaussian algorithm. We generate the mask and apply the DOG to the image, detect zero crossing and apply the threshold, and suppress if you have any zero crossings, display and exit. The last topic of this module, that is the Canny edge detection algorithm. If you see from the textbook, guys, there's a lot of algorithms, but for your syllabus you have to study only till Canny edge. So please make sure you don't study any extra topics, and because there will be a waste of time at least. So what is a Canny edge detection algorithm? This algorithm mainly balances the edge detection accuracy, localization, and the response consistency. So what it will do is it will combine your Gaussian smoothing. As we already discussed before, Gaussian will help you to smooth the image. It will help in gradient computation, non-maxima suppression, hysteresis thresholding to achieve the optimal detection results. So we are performing a series of various operations to achieve a best optimized result. So what are those series of operations? First we are doing is the Gaussian smoothing, followed by that we performing the computation, gradient computation, then we have a non-maxima suppression, and then we have a hysteresis thresholding. Then once you do all these things, then we maintain the edge continuity and we reduce the noise. So what is the performance criteria of a Canny edge detection? The performance criteria mainly says the good edge detection. We have three criteria. So one is good edge. We have good edge detection. It should accurately detect the real edge points while discarding the false ones. That means it should clearly. Okay, so next is the good edge localization. The good edge localization does is the detected edge point should be as close as possible to the close edge, to the true edges. Then we have a single response to each edge. The algorithm should avoid the multiple response to a single edge, eliminating the false and double spurious edges. So make sure that it doesn't have any false, double or spurious edge, and it has only proper true edges. So what is the algorithm? First we have a Smoothian filtering. Smoothian filtering, what we will do is we have to convolve the image with the Gaussian filter to smooth and reduce the noise. Okay, as discussed earlier, we already know that Gaussian filter will help you to smooth the image and reduce the noise. Followed by that, we compute the gradient of the smooth image to detect the edge orientation. Next, we store the edge magnitude in an array, for example m of x comma y, and the edge orientation in alpha of x comma y. So what you're doing is in Gaussian filtering, you just convolve the image, you apply the Gaussian filter, you smooth the image and you reduce the noise. Followed by that, we compute the gradient of the smooth image and we check for the edge strength and orientation. Followed by that, we will store each and every edge magnitude in an array. For edge magnitude we have m of x comma y, and orientation we'll store it for alpha of x comma y. So next is non-maxima suppression. In non-maxima suppression, what we are doing is we are thinning the edges as much as possible to produce sharp edges by examining the magnitude and the orientation. Okay, so what we are doing is we are approximating the gradient direction to one of the four sectors, reducing 0 to 360 range into four different sectors. So for each point m of x comma y, what we are doing is we are comparing the magnitude with the neighboring pixels. Neighboring pixel, suppose I say if my current pixel is m of x comma y, my neighboring pixel is m of x comma y and x comma 2. So we are comparing the magnitude of my current pixel with my neighboring pixel. Now if m of x comma y is less than m of x comma y1 or m of x comma y2, we are suppressing the value of m of x comma y by setting it to 0. That means that is all about the maximum suppression. We are suppressing the value and reducing it to 0. Next is hysteresis thresholding. Hysteresis thresholding is basically you are applying two thresholds, T1 and T0, and T0 is the low threshold, T1 is the high threshold, to differentiate between the strong and the weak edges. So what is the algorithm all about? If the gradient magnitude is greater than the T1, for example, the magnitude which we want to measure, it is greater than the threshold value, it is accepted, it's a definite edge point. Or if it is less than T0 value, that is low 1, it is rejected as a weak edge point. So for a gradient magnitude between these ranges high and low, we determine whether there is any part or edge on their context. Followed by that, we create two images using this threshold T0 and T1. The high threshold image will have a definite edge but may contain gaps. The low threshold might include noisy edge points. So what it says is basically once you apply all the gradient magnitude T0 and T1, you are getting the edge. Once you get the edge, you create the two images using the threshold T1 and T0 and T1. Therefore, the high threshold image will have the definite edges, but it may contain certain gaps, but the low threshold image may experience some noisy points, okay, noisy edge points. So basically we are bridging the gaps in the high threshold image by consulting the low threshold image, examining the 8 neighbors of each pixel to link the edges and form a continuous contour. So in order to form a contour of an image, what we are doing is we are examining all the 8 neighbors of a particular pixel, and we are linking the edges, and we are performing a continuous contour. So that's all, guys. In this all about module 5, we have covered the entire image segmentation, all the image processing algorithms, the different types of operators. So please remember all the matrices which I have discussed. If you have any doubts, please comment below in the comment box and let me know. And I will be releasing a series of all the important questions of digital image processing. Till then, please like the video, share the video, subscribe the channel. Thank you, guys.